So in this video, what I'd like to do is to go through exam R model exercises. I've put up here the document which is in week 3 of Brightspace along with this video. What I recommend is that you pull up the document and read along with. I have my own paper copy that I'm going to be using on the board back here. I'll be starting and stopping as we go along to put some material on the board and not spend all our recording time watching me scribe. So I'm going to get right to it. Question 1. So the first question, question 1, gives us a collection of sets, U, M, N, Q, R. U, for our purposes for this problem, will be the universal set, or the set of reference. M, N, Q, and R, by inspection, are all subsets of U. We are asked to find M cap R. That is to say, we're asked to find the intersection, M intersect R. And remember, the intersection serves as an AND operator. So what we're looking for when we're what we're looking for here is to find those elements of M that are also elements of R. Or you could say the elements of R that are also elements of M. It doesn't matter. They need to be the common elements of the two sets. So the easiest thing to do is to simply investigate from one set to see whether the elements of the other are also contained. If not, they aren't common, obviously. And once we've exhausted the elements in one set, we're done. Any other elements that might be available, again, are not common. So let's start with R. And, okay, again, M is the set of first 14 whole numbers, or 0 through 13. M is the set of the first set of 5 even numbers starting from 0, so 0, 2, 4, 6, 8. R, the set is the first 5 whole numbers, 0 through 4. M and R, what's common? We just, by inspection, determine what's common to the two sets. I'm going to use R as my starter set, reference set. 0 is clearly common to R and M, so that's certainly in the intersection. 1 is in R, but I can't find it in M. I dismiss it. 2 is in R and in M, so it is contained in their intersection, in their AND. 3 is in R, but it is not in M. We dismiss it. 4 is in R and in M. We include it. We've exhausted all the elements in R, so our search stops. It terminates. And we've determined the intersection of M and R. Just as a quick recall, what if instead we'd been given M cup R, or N union? Again, so people remember this is the intersection. M union R, or N O M or R. This is a union. Or the union asks us to construct the set whose elements are either elements of M or elements of R. So all we're doing is we are collecting, collating all the elements that are in either one of these sets. Work through it, just listing them off. In M, I'm just copying all its elements, 0, 2, 4, 6, 8. I move to R. 0 we already have, 1 is new, 2 we have, 3 is new, 4 is all we have, is already contained. The process terminates, we've exhausted the possibilities. Remember that the order in which we write the elements of a set does not matter. Any permutation of this collection of elements is a legitimate way to list the elements of the union of M, the sets M or R. The union of M and R. The last reminder, quick. M with the little hash mark. Remember, this means the complement of M. It's called the complement or the complementarity operator. And the elements in M prime, or the complement of M, are all elements contained in the universal set that are not contained in M. So we can think of it as a negation operator. It's sort of the set not M with respect to U. And we always have to have some universal or reference set to form a complement. We have to be able to say M is not in M, but in some such thing. M prime here, or the complement of M. M consists of 0, 2, 4, 6, 8. And U consists of the whole numbers from 0 to 13. So let's write the whole numbers from 0 to 13, except for what's in M. So we don't write 0. 1 is not in M. 2 is in M. 3 is not in M. So it's in the complement. 4 is in M. 5 is not in M. So it is in the complement. 6 is in M. 7 is not in M. So it's in the complement. 8 is not in M. Sorry, just making sure you can even see that. 8 is in M, so, well, it can't be in its own complement. 9, 10, 11, 12, and 13 are obviously not in M, so they're all in the complement. 9, 10, 11, 12, 13. All in the complement. Problem 2 asks us to evaluate negative 2 to the 4th. The point I want to emphasize, emphasize as I emphasized in class again and again, is we have to make sure we know whether that minus is within the scope of the exponent or outside the scope of the exponent. If the negative is within the scope of the exponent, we have parens around the entire expression, signaling to us that the entire expression is to be raised to whatever the power. We do not have that in this situation. So effectively, what we have written here, we could write equivalently as the negative of, put a paren, 2 to the 4th power, close paren. The negative is outside the scope of our exponential expression. 2 to the 4th, let's remember our rule. Fundamental definition. I'm not going to write all the conditions required. I'm going to expect you to remember what possible values for A, what legal values for A are, and what legal values we can use for N. But all we're saying is 2 multiplied by itself 4 times. 2 by 2 by 2 by 2, 2 by 2 by 2 by 2. It's clearly 16. Again, the negative stays, as it were, outside the scope of our operating. So now, simplifying, eliminating parentheses, we obtain minus 16. Question 3 asks us to find the product of the quantity minus 4 times x raised to the 5th, all multiplied by the quantity 4 times x squared. I suggest, first, we want to use our properties of real numbers to reorder the product as minus 4 times 4, group those times x to the 5th times x squared. We know how to multiply numbers together. We know how to operate with products of powers to a common base. Recall what that is. A to the n, a to the m. Again, I leave it to you to remember what a and m are. But we recall the product rule. The product of base to powers is the same as the base raised to the sum of the powers. Negative 4 by 4 is merely 16. X to the fifth, x squared, by use of our rule, product rule, is x to the fifth, x to the 5 plus 2, and we do the arithmetic. I'm going to drop the parens around the 16 times x to the 7th power. So we obtain minus 16 x to the 7th power. Question 4 asks us to find the product. The quantity 4r minus 1 being multiplied by the quantity 7r plus 2. Here we recall our FOIL technique, which we could think of as a double distributivity applied twice. First terms, 4r times 7r, 4 times 7 gives us 28, r squared. First. O for outside. First, the outsides, which will give us the first and the last. So we get 4r times 2, gives us 8r. Now we do the insides, as it were. So that's the second term of the first times the first term of the second. Minus 1 times 7r gives us minus 7r. And finally, L for last. We're taking the last term of the first times the last term of the second. And F, O, I, L. And we have minus 1 times minus 2. We recognize 8r and 7r to be like terms, and we combine them. 28r squared. Technically, what we're doing again, remember, is a kind of distributivity. So taking the extra step, we're pulling out the common factor of r, and then we're performing the arithmetic on our coefficients. 8 minus 7 is just 1. We generally don't write the 1 as a coefficient. It's simply, it's understood, it's implicit. And as I'm going again, I'm going to just stop and start the recording. I'll leave it to you to just stop the recording if you need more time to copy down what I'm doing. Problem 5 asks us to find the product, quantity 4x squared times the entire quantity of 3x cubed plus 2x squared minus 5x plus 1. To find the product, we merely need to distribute our 4x squared across all 4 terms of the polynomial within the parentheses. We get 4x squared times 3x cubed, I'll write as 12, and just for now I'll write 12 x 2 plus 3 as a reminder of our rule. Plus 4x squared times 2x squared is going to be 4 times 2 is 8 times x squared is the same as x to the 2 plus 2 power. Minus 4x squared, minus 4x squared times 5x gives us 20. X squared times x gives us x2 plus 1. Plus 1 times 4x squared is just 4x squared. I do the arithmetic on the exponents. That is a 2, not a z. 12 x fifth plus 8 x fourth to the fourth minus 20 x to the third plus 4x. And we're done. Question 6 asks us to use the formula for a binomial squared to multiply 4m, quantity 4m plus 2n raised to the second power. What is the formula for a binomial squared? Well, what do we mean by a binomial squared? Something like that of the form x plus y squared. What is our formula for that? Remember, that's a perfect square trinomial. Asked you to memorize the form of a multiplied out perfect square trinomial. Multiply it out. To do that, as we have a square, by definition, x times y, quantity x times y, but times quantity x plus y times itself. Foil it out. I'll let you foil it out. You should find x squared plus 2xy plus y squared. Again, the formula for a binomial squared that you should remember, recall, and apply. I'll just write it out here again as we're going through. 2xy plus y squared. Now, also recall, or again, do the work. If instead of a plus, it were x minus squared, and we had a difference, a binomial difference squared, recall that we find that what happens is the sign of the middle term or the mixed term goes from positive to negative. So now, in our case, 4m plays the role of x, 2mn plays the role of y. And so as it were, applying the formula rather than actually foiling out, what do we see? We see that our x is squared, so that's our 4m in our translation. 4m is squared plus 2 our x times x, which is 4m times n times y, which in our case is 2n, plus y squared, what plays the role of y? 2n. So we have 2n quantity squared, okay? Now that I've taken advantage of our correspondence, we've done all we need with that. I'm erasing it. You can all, remember, stop the video if you need to see it for longer. Equals, and now we just multiply out. 4m squared is 4 squared m squared. 4 squared is 16, m squared. Plus, I have 2 times 4 times 2. Again, I'm going to take this extra step. Remember, by applying our properties of real numbers, which we extend to polynomials that have real coefficients or integral or rational coefficients, we have the same nice properties. So we can just rearrange the order of our multiplicand. So 2 times 4 times 2 times n plus the last term, just like the first, 2n squared. 2n times 2n gives us 4n squared equals 16m squared. 2 times 4 times 2, that's 16 again. mn plus 4n squared. And hopefully you don't catch me having made a silly arithmetic error, which in fact I do. So if you think I have, definitely send me an email and say, Joe, I don't think you did your arithmetic correctly. And I think I did. Problem 7 asks us to perform the indicated operations on the given difference of two polynomials. I'm not going to read it out this time. Let's note first, just again, the sort of thing that in general we just implicitly take for granted. But in some sense, there's always a 1 times out in front of a paren of this form. And then when we have a minus something, that's the same as saying plus minus 1 times whatever. Need to remember, this is useful, that subtraction of something is the same as plus 1 minus 1 times something. In each case, what we're doing actually is distributing. But in the first case, 1 times whatever is just what it is. So there's no work to do. And in fact, we could say the parentheses are superfluous. For the second term, we do have to be careful. As we're distributing, again, remember when we distribute, we must distribute to all terms. I know I've said that too many times already, but I also know that many times when people are working quickly, they forget to distribute to all terms, and they tend to just distribute to one or the first few, and then for whatever reason, forget to follow through. And we distribute to all terms. So the minus 1 is distributed through to the first term, which gives us a minus. Let me be consistent. Say a plus gives us a minus 3p squared. Minus 1 times 2p gives us a minus 2p. Minus 1 times 7 gives us a minus 7. At this point now, again, a 1 implicit, the parentheses are superfluous. Again, I'm going through these steps sort of call it an overabundance of caution. I'm not expecting you to have to go through all of them. If you feel comfortable just saying, I pass the minus through to all terms, that shorthand is fine. Mental shorthand. Now what do? Remember, we collect like terms, which itself is, again, a shorthand for we apply the properties of real numbers as extended to our polynomials so that we can, as it were, rearrange in whatever fashion we like the sum or difference, as long as we respect the role of our negatives. So what do we have? Let's collect our terms according to the degree of the polynomial, the degree of the term. We only have 1p cubed. I'll leave that there. Then we have a minus, I'm just rearranging now, a minus 4p squared and a minus 3p squared. So I'll just bring those together. And then I have p to the first power here, minus 2p to the first power there, minus 7. Okay. Without going through all the silliness of, continued pedantic silliness of putting things in parentheses and taking them out, we will now perform the arithmetic on like terms. Minus 4, minus 3, we add the coefficients and keep the power. So what do we have? P squared minus 4 minus 3 sums to minus 7. Likewise, 1p minus 2p, 1 minus 2 sums to minus 1. So we have a minus 1p or just minus p, minus 7. Problem 8 asks us to factor the trinomial x squared minus x minus 56 if possible. I'm going to imagine that most of you can probably eyeball this to see what the factorization into a pair of linear factors should be. Since so many of you probably can, I want to make it a point to apply our AC method or our algorithm just for the practice, because it's always good, in particular, it's good to practice an algorithm you may not, or technique that you're not comfortable with in a context where you know what should be coming out through other means. If you're confident about the result, then, but uncomfortable with the technique, use the technique where you know what's going on, because then you figure out how to make sure it works in all cases. Okay, anyway, we're looking at something of the form ax squared plus bx plus c, where here a is 1, b is -1, c is -56. And according to our method or algorithm, what we do is we consider the product of the lead and constant coefficients, which here is 1 and -56 equals -56. And we look at possible factor pairs of -56 and ask, does there exist a factor pair Mn of -56 such that the sum of those factors equals our linear coefficient, which in this case is -1. To do that, we have to run a search on factor pairs of -56. And in each case, we look to see what the sum is. If we find something that works, remember, we halt the process immediately. So, easiest factor pair besides 1 and 56 I can think of is going to be, I want -56 and I want -1, so I'm going to take an absolute value, the negative number to be larger, -8 and 7. Add it up immediately. -8 and 7 gives me -1. Exactly what we want. Stop, stop. Don't search any longer. The fact that we have a success means our original quadratic trinomial does have a factorization into a pair of linear factors with integer coefficients. Now we're going to find that factorization by using the fact that we've seen that b -1 can be expressed in the form -8 plus 7. We replace the expression for b -1 with the expression -8 plus 7 in our original equation. So again, let me be a little bit pedantic, but careful. This is our original, x squared minus x, which I've written as plus -1 times x, -56. This is equal to x squared plus, now I replace -1 with -8 plus 7, x minus 56. So here's our replacement step. Next, what do? We distribute. So I'll call it our expansion step. We expand. We expand or distribute. When we do that, what do we get? X squared, sorry, that'll be x times -8, -8, x times 7 plus 7x, minus 56. Our next step, we group. We group our first pair, our second pair. Now what do? Well, we factor out whatever is call it the GCF of the terms within each grouping. Sorry, I'm running out of space here. Here I have an X is common. That leaves me an X in the first term. I'm left with an 8 in the second, plus here I have a 7. That's common. Take the 7. I'm left with an X in the first term, and to get minus 56, I've got to pull out an 8, which is what we'd expect. This is why we did this. We now have a common factor of X minus 8 between our two terms. For a moment, let me use this stretch. So after factoring, now we said we take out the X minus 8 equals X minus 8. And what do we have left in that first term? An X. What do we have in the second term? Plus a 7. And so, in fact, many of you had probably, now rolling your eyeballs, had eyeballs at the very beginning, said, yeah, Joe, we see it factors as X plus 7, X minus 8. I'm sure many of you did, but I'm also fairly confident that for many of you, this process is like an old practice that you just got to get back into. Like anything. If you don't keep up with the exercise, then you have to reacclimate the body, the mind, the whole organism to it. So, question 9 asks us to simplify this expression and tells us to write our answer without negative exponents. And we assume all variables represent non-zero real numbers. First thing I would urge you to notice is the 0, and ask yourself, remind yourself, what is any non-zero base written to the 0th power? Universally, that's 1. It doesn't matter what the base is, as long as the base is a legitimate base. Any such base to the 0th power is always equal to 1. So, not caring what's inside, we don't need to. We simply know that anything like that to the 0th is 1. But we still have to deal with the negative exponent. How is a negative exponent defined? A negative integral exponent in this case. We take n to be a positive integer and define a to the minus n to be the reciprocal of a to the nth power. So that means that, just isolating for a moment, to remind ourselves that means that p to the minus 4th is alone, not in context, alone, by definition, is 1 over p to the 4th power. Okay, knowing that, apply it in context. 1 over 5. Let's do it this way. Let me try this. No, I'll go through this way, and then I'll actually do it a second way. 1 over 5 And we apply our definition. 1 over p to the fourth gives us 1 over 5 over p to the fourth. How do we simplify this kind of complex fraction? Remember the usual rule, the only rule. The rule would be take the reciprocal of the denominator and multiply numerator and denominator by that reciprocal. Sorry if my writing is getting too small. Over p to the fourth over 5. Okay, so as I'm multiplying, 5 times p to the fourth time, multiplying 5p to the fourth by p to the fourth fifth, what have I got? I've got a 5 in the numerator and denominator, which cancel. I've got a p to the fourth in the denominator and the numerator, which cancel, leaving me a 1 in the denominator. We obtain 1 times p to the fourth over fifth over 5 over 1. Anything over 1, we disregard that denominator. 1 times anything is just itself. This reduces to p to the fourth over 5. I'm going to erase this, do it another way. Pause the video if you need more time. We extended this rule from positive integers to basically any rational number. So 1 over this we can think of as 1/5 times 1 over p raised to the -4th power. Now what I want to do is take 1 over p to the -4th power and apply our definition where now n is -4, because remember, we extended our definition to all rational numbers. -4 is a rational number. So by the extension of our definition, where now n is -4, then reading from right to left, we obtain that 1 over p to the -4th is equal to p to the -4th. And a minus is a positive. So this gives us p to the 4th over 5. Question 10 asks us to perform the indicated operation. Assume all variables represent positive real numbers. Sorry, just checking that the board is legible. Yeah. X to the 1/4, y to the 2/5, quantity to the 20th, all over x squared. First blush, this looks like we're dealing with a somewhat different animal because we're dealing with rational exponents. But we recall that the rules of exponents working with rational numbers are basically the same. They are the same as the rules of exponents working with integers. We extended the rules on integers to rational numbers by the way we defined, in particular, a to the 1 over n, which at this point I don't need to even remind you of, because given that the rules are the same, we can simply apply the rules to this situation. What rule? Well, that's the rule. That's what we need to recall right now. A times b to some power n is equal to a to the n, b to the n. In this case, let x to the 1/4 power play the role of A, and let the role of B be played by y to the 2/5 power. Then n is 20, and we can immediately write x to the 1/4. Sorry, that's going to be too small. X to the 1/4 to the 20th, y to the 2/5 to the 20th, all still over x squared. Now, what else do we have to remember? How do we handle the case where we have a base to a power that we raise to a power? That power rule tells us that a base to a power raised to a power is equal to the base raised to the product of the powers. Two of our so-called power rules. So we're applying two versions of the power rules here. So applying the power rule to this situation, we obtain x raised to the 1/4 times 20, y to the 2/5 times 20, all over x squared. Do our arithmetic on our exponents, 1/4 of 20. 1/4 of 20 simplifies to 5. 2/5 of 20 simplifies to, or 40 divided by 5 simplifies to 8 over x squared. At this point, I'm going to just insert the extra step, as it were, putting together our numerator and denominator are like variables, as it were. There's y to the 8th. Why did I do that? Because again, remember, x squared, as we defined it, is the same as x to the -2. Y to the 8th. And then from here, what do we use? We use our product rule. We have 5 plus a -2, which is 5 minus 2 times y to the 8th. 5 minus 2 simplifies to 3. Oh, I'm sorry. I thought I had paused the recording, but I didn't. So, a little waste of time there. Hopefully I can edit it out. Problem 12 asks us to evaluate the expression. And clearly here, we have to apply the order of operations. We have no PE in PEMDAS. We have no parens. We have no exponents in this case. So we start with the MD, the multiplication and division. We perform the multiplication and division as we encounter it from left to right. -2 times 5, -10. We, as it were, skip over the addition for now. Encounter 12 divided by 3, it's 4. Having completed the MD, we're now left with the AS, the additions and subtractions. -10 plus 4 is -6, and we're finished. Problem 13 asks us to evaluate the expression that I've written here This is another application of PEMDAS. So a certain extended version of PEMDAS, just have to remember to work with the numerator and denominator of the fractions separately. Looking at the numerator, we have -8 plus -4 times -6. So here's a multiplication. -4 times -6 divided by 12. As we have a plus, we're, as it were, skipping for now, and we're going to complete the multiplication and division from left to right. We encounter the multiplication. -4 times -6 gives us 24. I'm going to leave the divide by 12 right now. We'll come back. We'll do the division. I would like to advance, as it were, the presentation of the denominator. I have 4 minus -3, so that would be 4 minus the minus is plus 3. I still have a division, so I leave the -8 plus 24 by 12. Divide by 12 is 2. Now I'll simplify my denominator as 7. -8 plus 2, that's all we have left in the numerator now. Add it up, -6. Nothing left to do in the denominator, 6/7. Problem 14 asks us to let x equal -13, y equal -10, and evaluate the expression, the absolute value of the quantity 2x minus 5y. First thing we do, I'd say before we ask the question about what is absolute value, is we simply substitute in for x and y and see how far we get with that. 2 minus 13 minus 5 times -10, quantity squared, quantity absolute value. 2 times -13 is -26. -5 times -10 is plus 50. So I get 50 minus 26. Well, 50 minus 25 would be 25, and one more subtracted leaves me with 24. Now, what is the absolute value of 24? Briefly, just to recall, given a real number, the absolute value of that real number is itself if it's at least 0. And it is the negative of itself otherwise. That is to say, if the number inside the absolute value is negative. That's how we ensure that absolute value is always, the output of an absolute value is always non-negative. Here, 24 was already greater than 0. By our definition, the absolute value is simply 24. As long as I didn't mix up my variables or my addition, we should be good. Okay. Question 15 asks us to factor out the greatest common factor from the polynomial as given. One thing I do want to mention is that I get the impression from some people that as they're asked to, as it were, factor out as they're asked to factor out the greatest common factor, they somehow think that they have to do it in one fell swoop. If they don't pull everything out all at once, they've somehow committed a mistake. No. If you withdraw what you think is common, the greatest common factor, and you look at what's left and see that there's more common, we simply take another step and withdraw what remains common. There's no error in that. So I'm going to actually do that. I obviously see an a plus b common to both terms, and so I'm going to, as it were, withdraw it on the right. I have a 6x left minus a 4x. Now where I am mistaken is if I say, because I took the a plus b out, I'm done. I don't know whether I'm done. I know the a plus b is common, but I need to look at what's left, as it were, and see whether there's any more I can, so to speak, withdraw or remove, pull out. And as 6 is 2 times 3 and 4 is 2 times 2, I see that there's a common factor of 2 between these terms, because obviously x and y are not common as they're independent transcendental variables. But we can, as it were, pull out a common factor of 2. I'll do that to the left. 2, I'm left with 3x, 2 times 3x gives me my 6x back, minus 2 times 2y, times a plus b. Now, that's fine. The only thing I'm thinking about is in MyMathLab, it may be a little bit finicky and want you to write it in the form of 2 times a plus b, where we take and put the greatest common factor off on the right. But I will say, if you put an answer in this form, and MyMathLab were to tell you it's wrong, when I review your exam, I will override MyMathLab's determination. Because you have indeed, in this case, factored out the GCF. You just haven't put it in a form that MyMathLab recognizes, but it is an equivalent and so correct form. For number 16, we're asked to factor the quadratic trinomial 9m squared minus 12m plus 4 if possible. So by if possible, this means we have to first determine whether indeed this factors. I just want to run a quick check to make sure that there isn't a common factor we could withdraw. There isn't. Good. So we have to run our algorithm to test whether or not it's possible, whether there is a factorization. So I'll say AM plus BM plus C. Remind yourself in that form where now A equals 9, B equals minus 12, C equals 4. So by our test, what we want to do is look at the product of the lead and constant coefficients, AC, 9 times 4, 36, and see whether or not we can obtain a factor pair MN such that it satisfies the relationship B, which is minus 12, equaling their sum. So in order to do that, again, technically what we would do is we would go through an exhaustive list of factor pairs. Again, since our B is negative and our A and C are positive, we can perhaps use those facts to narrow down the number, the size of our search. But if we don't, we just run through all possible factor pairs and see what the factor pairs sum to and see whether or not we can obtain minus 12. In this case, I think it's fairly easy to see that if I took M to be minus 6 equal to N minus 6, the product is going to be 36 and the sum is going to be minus 12. So this tells me I can express B in the form of minus 6 minus 6. So what we want to do now to effect the factorization, make sure that we present the trinomial in a way that we don't confuse ourselves. 9m squared plus the minus 12, which is our B, m plus 4. We replace the expression for B. We replace minus 6 for the coefficient b, the expression minus 12. Minus 6m plus 4. I'm going to write it out this way. We expand this term. It's 9m squared minus 6m plus 4. Factor. Group. Let's group. 9m squared plus, minus 6m. Let's do minus. Could do plus or minus. Minus 6m. Having taken the minus, let's be careful. The sign in front of the 4 is a plus, but since I've, as it were, pulled out a minus 1, we may have to switch the sign in front of 4. Again, when you go about multiplying out the minus 1, we will recover a minus 6m and a plus 4. Okay. So now, how do we factor each of these terms in the paren? I've got an m common, 9, 6 are both multiples of 3, so I take a 3m. I'm left with a 3m minus, well, the m is withdrawn, and 3, factor of 3, so I'm left with 2. Minus, what do we have here? What's common? 6 is a multiple of 2, 4 is a multiple of 2, 3 times 2, 2 times 2. I can pull out a 2. Leaving me a 3m in the first term. Sorry, I should get on this side. And leaving me a 2, a minus 2. Sorry. There you go. Minus 2. Which, of course, we need a minus 2. We're looking to obtain a common factor. I wouldn't want to go through all that process and then not be able to withdraw a common factor. Defeats the purpose. So good arithmetic is required here. All right, we have a common factor of 3m minus 2. What remains of our first term is a 3m. What remains of our second term is a minus 2. Now, doesn't this look strange? So, what does that tell me? What does that tell me? This should remind us of something, right? We already saw properties of these binomials squared, sum or a difference. So, this suggests that we might have approached this problem in an entirely different fashion. So, if you're still working on this, pause the video, because I'm about to erase it all. We're going to work the same problem through from a different angle. And even though we can do it in this other way I'm about to show you, I think it's vital to every opportunity you can to practice this method, to get it, to develop facility. But here's the other way we can do this problem. Maybe, oh my good chalk. Here we go. I'm going to rewrite this like we did in the class with a couple problems as, I noticed 3. Let me write it this way. 9 is 3 squared, m squared minus, I'll leave it as 12m for now, plus 4 I can write as 2 squared. That's ringing in bells somehow. 3m quantity squared minus 12m equals 2 squared. This is starting to sound like it might be one of those special factorizations, like a perfect square trinomial. All I'd need to do, if that's true, is to make sure that that middle term has the quote-unquote right form. So to see whether it does, let's extract a 2, and that leaves 6m plus 2 squared. And now if that is going to give us the right form, we should be able to rewrite this in the middle term as the product of what's in the parentheses here and here. And indeed, I can rewrite 6m as 3m times 2. Let me add the 2 squared again. Aha! Perfect square trinomial with a perfect square binomial with a difference. We know the rule first, so what plays the role of x minus what plays the role of y, quantity squared. Two very different ways to get the exact same result. I mean, neither is the correct way. Both are useful in various contexts. One or the other might be exactly what you want. And for speed, I'd say recognizing the form of the factorization, this is a special form, is quicker than trying to go through the AC method. If you don't happen to see if you don't happen to recognize it though, the AC method gives us a foolproof way to proceed in these sorts of circuits. Problem 17 asks us to write this rational expression in lowest terms. Well, like with fractions, to write them in lowest terms, we need to fully factor our numerator and our denominator, and then observe common factors, if there are any. So we have to factor our numerator, factor our denominator. If this numerator factors, notice that the coefficient of our lead term is 1, which means that our linear factors are going to have to look like y plus or minus something times y plus or minus something. And those plus or minus somethings have to sum to 18, right? The product have to multiply to 18. So just by exhaustion, we've got something like 1 and 18, or 3 and 6, or 2, I should do it more carefully, 2 and 9, 3 and 6, and what else? Nothing else. Sorry, rhetorical question. Clearly, we're not going to find a way to we're not going to find a way to get a -7 in the sum of 1 and 18. No matter how you try to add or subtract them, you're not going to find a -7. They don't add to -7. 3 and 6. Well, no matter how I try, if I took both negatives, I'd end up with a -6 minus 3 for -9. If I try to mix them, one positive negative, I'm going to obtain nothing less than -6. So 1 and 18, no good. 3 and 6, no good. The only possibility left is the factor pair 2 and 9. Is there a way to add or subtract the 2 and 9, come up with a -7, and multiply them together to get an 18? Well, to get the -7, it certainly looks like I'm going to have a -2 and a plus, -9 and a +2. That satisfies our middle term. But what happens when we multiply out? We get a negative 18. So what does that tell us? It seems to be telling us that this numerator does not factor. Let me just make sure, double check. I'm going to pause just to make sure I'm not making some foolish mistake or have written something incorrectly. Then we'll proceed. Okay, I don't see that I wrote anything down incorrectly, and our analysis was correct. So what we've discovered is that the numerator is irreducible or prime. As it's prime and it's of second degree, again, it doesn't factor into any linear factors, then no matter how the denominator may factor, we could work it out, but why bother? Because no matter how it factors, those factors cannot be factors of the numerator. Why? If they were, the numerator would factor. And what we've seen is that the numerator does not factor into a product of linear integral polynomials. So this is, in this case, this polynomial is already expressed in lowest terms. Now, perhaps a less trivial example. Hold on. Okay, so I want to do another example. This one I've rigged to make sure that it does factor so that we actually get some practice. I think it's important both to see examples where there is no non-trivial factorization because one of the numerator denominators already prime or irreducible. But again, I think you're more likely to get an example like this where it does factor. So here, again, either by inspection or through the AC method, our numerator here will factor as, I believe it will. Don't trust me, FOIL it out. We get y squared minus 9y plus 2y minus 18 minus 9y and 2y sum to minus 7y. So, okay. So my factorization of the numerator is correct. It's not equal yet. Factor the denominator. Process similar. Likewise, obtain y squared. By one method or another, we determine that the proper factorization of 24, that will obtain 14, as our linear coefficient is y plus 12 times and y plus 2. Again, FOIL it out. Y times y is y squared. Y times 2 is 2y plus 12 times y is 12y combined to 14y. Plus 12 times 2 gives us 24. All right, so we have a complete factorization of our numerator and denominator into its linear components. In this case, we see a common factor of y plus 2, which we can cancel. So I say equal now. And now, so reduced, we have 9 minus y in the numerator. We have 9 plus 12 in the denominator. Problem 18 asks us to use the product rule to simplify the given product. I believe this looks like one we've already seen. That's okay. So similar to the last time we saw this problem, we've got a product. So we can, using our properties of real numbers as extended to polynomials, with coefficients that are integral or rational or real, we can apply the same rule. So we rearrange the order of our multiplicands. -6 times -3, as it were, taking grouped together like with likes, as it were. Group together the 8th power of x with the 7th power of x. And here's, we apply our product rule. Our product rule is given here. Base to the nth power, base to the nth power is the same as base raised to the sum of the n plus mth power. -6 times -3, a minus is a positive. 6 times 3 is 18. Applying the product rule, we then have the sum, 8 plus 7, x to the 8th times x to the 7th is x to the 8th plus 7th. Do the arithmetic, 8 plus 7 is 15. Problem 19 asks us to perform the indicated operations. Here we're asked to add two rational expressions. Again, just as we were adding fractions, same rule applies, same basic rule applies. Product of the denominators, and then our numerator becomes the original numerator times the opposite denominator plus original numerator of the second times the opposite denominator. So again, two ways to approach this. Either, as it were, multiply each to obtain a common denominator, multiplying numerator and denominator, again, a form of 1, or just directly apply this form of the definition of the addition of two fractions. We do that, what do we have? Taking this to be A, this to be B, this to be C, this to be D, my denominator becomes, and again, we're not worrying about least common multiples or least common denominators here. We're strictly applying the fundamental definition. 15x times 21, x squared, that's BD. A is 4 times D, which is 21x squared, plus, or it could be minus. So it could be plus or minus. Plus 6, which is our C, times B, which in our case is 15x. Now I'd say instead of multiplying everything together, what we do is look at the numerator, factor out everything we can. Look at the denominator, factor out everything we can. See what's common, cancel it, and then worry about any final computational requirements. So out of 4 is a 2, I find a 2, and 6 there's a 2, so that's in common. So I at least have a 2 out front. I have a 3 from 21 and a 3 and 6. So I can, as it were, pull a 3. A 3 is common to both terms. Then all that remains in this, as far as coefficients, is another 2 and a 7. I don't have a multiple of 4, so I only had the 1, 2 from the second term, and 15 is surely not a multiple of 7. We do have a common first power of x, which we can extract as well. What are we left with? I took a 2, and so that leaves a 2 of the 4. I took a 3 from 21, leaves 7. I took 1 power of x, leaves 1 power of x. I took 2 times 3 out of the second, which is effectively, I took 6 out, which leaves and an x, which leaves me 15. All divided by. What can I take as common from here, as it were? Well, it's a product. It's a product. So what am I going to do? I can pull out a 3. I can pull out an x. And what am I left with? 5 times 3 for 15. There's my x times the rest of what's in the denominator, 21 x squared. Double check. All I'm doing is multiplying out, so I'm just sort of regrouping the multiplicands. Having done that, what do I see to be common? A 3 is common, an x is common. Those cancel. Nothing else that remains is a common factor. So we're done. We've got 2 times 7. I can do the multiplication out now, I suppose. 2 times 7 is 14x plus 15 over 21 by 5, 105 x squared. And if we multiply the 2 through, we get finally 28 x plus 30 all over 105x squared. And we have thereby performed the indicated operations. Problem 20 asks us to factor the polynomial 49x squared minus 81. We could attempt to use the AC method, but I would suggest that we sort of squint and see whether or not there's a special factorization, a special product that we might be able to apply in this case. Let me write it this way again. 49 is 7 squared. 81 is 9 squared. Everything there is squared, squared, squared. So I have 7x quantity squared by our power rule minus 9 squared. So what is this? This looks like something of the form a squared minus b squared, a difference of 2 squares. That's a special product that you need to memorize, should have memorized. And its factorization, as we've seen, is given by the a plus b quantity times quantity a minus b. You check it by foiling. Foil this back out, you'll recover a squared minus b squared. So given that 7x plays the role of a and 9 plays the role of b, we can immediately factor as 7x, if I can keep the chart, 7x plus 9, 7x minus 9. And we're done. Recognizing this is a special product, a difference of 2 squares, we immediately obtain the factorization if we have memorized it. Again, if we haven't, this is a quadratic trinomial. It has the form 49x squared plus 0x minus 81. We suppress the linear term if its coefficient is 0. But in fact, you could say this quadratic polynomial does have a linear term. It's just that it has a linear term with coefficient 0. Thinking of that as b, here's your AC. 49 times 81, go for it and try to figure out a factorization. But you'd better recognize that 49 is 7 squared and 81 is 9 squared, or you're going to be doing a lot of factor pair checks. Problem number 21 asks us to find the product that's written here. Again, as far as it goes with rational expressions, just like with ordinary rational numbers, when it comes to multiplying, we multiply numerators together, we multiply denominators together. And similarly, oftentimes what we want to do Well, yeah, oftentimes what we want to do is to assess whether or not there are factors common among numerators and denominators. So what I propose is, let's see what factors. And clearly 10p minus 10, those terms have a common factor of 10 is p minus 1. And as I do this, I'm going to just sort of continue as one fraction, as it were, creating the right-hand side here. So we're multiplying that by 11 p cubed, denominator, p squared times, clearly we have a 5 common, and what's left is again p minus 1. Now, immediately we see the p minus 1s are common, so we can cancel those from numerator and denominator. Since this is n, this is times, always times here. We have a factor of 5 in the numerator, in the denominator, a factor of 10 in the numerator. 10 is 5 by 2. The 5s cancel. Let's see where we are just now. We have a 2 left and an 11 for 22. P cubed in our numerator. In our denominator, we've canceled the 5, we've canceled the p minus 1, we're left with a p squared. Again, you don't have to do this step, but I would recommend it if you're not completely comfortable with working with exponents. I've noticed we can rewrite this as 22 times the rational expression p cubed over 2p cubed over p squared. And from here, we recall, again, our power rules for quotients. No, sorry, I don't mean the power rule, I'm sorry. A to the n over a to the m. Quotient rule, this gives us, again, thinking of this as a to the m times a to the m minus m. Sorry, I'm getting tired here, I apologize. N times a to the n minus mth power. Apply our product rule. Now the sum becomes a difference, a to the n minus mth power. So again, having we're grouped these multiplied, we now apply our rules of exponents and obtain p to the 22 times p cubed minus 3 to minus 2. 3 minus 2 being 1, we're left with 22p. Now, someone could say, look at the beginning and just say immediately, I see from the multiplication that I can cancel a p squared, leaves a copy of p upstairs. 11, do the factorization, sort of instantly see that 10p minus 10 is double 5p minus 5. Just cancel the 5p, cancel the 10p, leaves a 2. And that would be a perfectly valid way to proceed. Again, I've worked through formally in accordance with what we have developed over the last 2 weeks. What I'm about to show you is writing out what I just said for the person who says, I don't see why I need to go through this process. Again, if you're comfortable working with these sorts of expressions, again, let me repeat myself. What I was saying is, one could immediately observe, I have a p squared downstairs and a p cubed upstairs. So the p squared cancels against the p cubed, leaving me with 1 power. 10p minus 10 is just 2 times 5p minus 5. If you recognize that, then 5p minus 5 cancels immediately with 5p minus 5 upstairs. What am I left with? Nothing in the denominator but 1, so we'll ignore it. In my numerator, I have 2 times 11 times p, which is 22p. So again, if you're comfortable working with polynomials as if they were just integers, you don't necessarily have to go through all the steps that I showed you. But if you're not comfortable, I recommend you do go through these steps to make sure that you apply the rules properly. Going through the steps also means that you do directly need to recall and practice the rules of exponents. And if you don't have those down cold, I would suggest putting problems in your way that give you an opportunity to practice using the rules, practice recalling the rules as much as possible, because we're going to be using them throughout the semester. And at the end of the semester, when we work with exponential functions, in some sense, exponentials and logarithms going to be nothing but working with these rules of exponents. If you don't have them down cold by then, you will wish you had. Lastly, problem 22, factor out the greatest common factor. Simplify the factors if possible. So actually this problem number 22, I don't frankly see the difference between this and problem 15, which we covered. So in some sense, this is just repetition, but that's fine. Immediately we see 7x minus 3 as a common factor to the two terms. We, as it were, pull out 7x minus 3 from each term. What are we left in the first term? 4x, plus what we're left in the second term, which is 3. 7x minus 3, no common factors between 7 and 3. There's nothing, this doesn't further reduce. 4 and 3 are relatively prime, so they have no common factor greater than 1. So that doesn't reduce. We're done. And with that, I think we have worked through the entire model exam. Oh, no, we have one more problem. What am I saying? Number 22. Give me a chance to write something down. Okay, last question. 22 asks us to match the expression in column 1 with the equivalent expression in column 2. Choices may be used once, more than once, or not at all. I'm not bothering with column 2. Those are your answer choices. I'm just going to work through column 1 to see what the correct answer actually is. So, 4 to the minus 2, recall the definition of a negative integral power. A to the minus n is equal to the reciprocal of a to the nth power. So the reciprocal of a to the nth power here is 4 squared. 4 squared, 16. So write it out as 1/16. B, we've seen this case already. The minus is, so to speak, outside the scope of the exponent. We could, in fact, write this as minus paren 4 to the minus 2 power. The minus outside 4 to the minus 2 power reduces to case A, which we know is 1/16, with a minus out front, minus 1/16, or just without the paren, minus 1/16. C. In this case, the minus is within the scope of the exponent. Let's be careful to apply the definition correctly. So the definition tells us what? quantity negative 4 raised to the minus 2 power is the same as the reciprocal of the quantity minus 4 squared. Minus 4 quantity squared. Well, the square of minus 4 is the same as the square of plus 4. And 1 over 4 squared, we already saw, was 1/16. So in fact, what we're saying is it's equal to 1/16, is that the quantity minus 4 to the negative 2 power is equal to 4 to the negative 2 power. All right. And what do we have finally in D? The first minus sign lies outside the scope of our exponent. The scope of our exponent is defined by the parentheses. The parentheses define the scope of our exponent. So the minus stays outside. We could write this as minus, this looks a little funny, but bracket minus 4 raised to the minus 2. Sort of like we did here, except we didn't need the square brackets to differentiate from the round brackets. Equals the minus stays outside. What's inside? Notice that what's inside here is exactly what we did in case C. And we found in case C the answer to be 1/16. So minus 1/16. Eliminate the brackets, that's just, or the parens, the square parens, that's just minus 1/16. Minus 1/16 is the same as what we found in B, which means that minus the negative square of the quantity minus 4 has exactly the same value as the negative of the quantity 4 raised to the minus 2 power. Knowing the rules, knowing how to apply them, when I say the rules, what I'm basically saying is the definitions. That's all we're working with here, definitions and understanding how parens work, understanding what the scope of an exponent is. Understand that, you do the operations quickly, and you identify which items in column B correspond to the items in column A. And you'll notice that only 2 of the 4 choices are ever used in this case. So you can expect to see a problem of this type on the exam. And with that, now I have completed a review of all the problems. I will soon hopefully get an answer key up as well. Take care.